there are a couple different ways we can figure out where images form when we're dealing with spherical mirrors. Right. Now, the first method that we're going to look at is a geometric method called ray tracing. This is going to be a qualitative way we can figure out where the image is, and it's going to be approximate more than because we're going to be just drawing lines and whatnot. So we won't be making exact measurements. We'll just be drawing lines and making a good guess about where something is. Now, so let's say we've got a mirror and we have an object in front of that mirror. For simplicity's sake, we're typically going to make our object so that one end is on the principal axis and the other end is extending somewhat up. And we'll just, for the moment, I'll just draw an arrow. That's going to be my object. Got a little arrow. Okay. And I am actually going to use a ruler, and that you also use a ruler in order to, number one, get straight lines, and number two, to know where the focal and the center of curvature are located. So I'm going to estimate about where my center of curvature would be. Maybe right about here, my center of curvature, and that is some distance. The marks are kind of worn off, but I can go, that's like 3.2-ish, so I can go 1.6 and get my focal point right here. Once I have those, I can just draw straight lines. Okay. There are three rays that we're going to draw to figure out where our image is. There are three rays that are typically used. There is the P ray, and that is a horizontal ray. It's called P because it is parallel to the principal axis. So that is the ray that's going to come off this arrow horizontally and hit the mirror. Okay. Then there is also the C ray, and that is the one that goes toward the center of curvature, and the F ray, which goes toward the focus, the focal point. Alright. Now, in this case, we have a convex mirror. This is our principal ray. Our C ray will point toward, will travel along the path toward the center of curvature, and our F ray will travel toward the focus. Now these are all pretty close together, so maybe I should have made a bigger picture, but oh well. Now what's going to happen? Well, what happens? The P ray is bounced back along the line that goes toward the focal point. So the P ray will go back this way. And I'll extend that line. Alright, so that is where that one is going to go. Now the one heading toward the focal point will kind of do the opposite. It will bounce back horizontally. And the ray that is initially traveling toward the center of curvature will continue heading straight toward the center of curvature. Or will bounce back along the same line, I should say. Now we notice what happens. These three rays, look at this, I'm so proud of myself, all converge in a single point. And this point then corresponds to the point on the image that goes with the point on the actual object. So in this case, our image will be right here, and it will be that will be where the image of the arrow is. Now, there isn't actually anything here. The rays are all bouncing back, but what's happening is this is where the object appears to be, as though if the object was right here and there was no mirror, you'd see kind of the same thing. So this image, number one, there aren't actually rays converging. So this is known as a virtual image. It is also upright. It's not flipped upside down. But it is virtual because rays do not actually converge. Rather, our eye kind of traces them back, and it appears as though they're emanating from that source. Right? So that is what a virtual upright image means. We can also note here that we only actually need two of these rays. They all converge at the same point. We only actually need two of them to determine where we're going to be, but the third one is useful to have as a check. Now, this is for a convex mirror. For a concave mirror, there are several different cases we need to consider. For a concave mirror, there are several different cases that we need to consider. The first we're going to look at is for an object that is out beyond the center of curvature. So we'll say we're out here. Right? We perform the same ray tracing shenanigans. We've got our P ray, which goes out horizontally and bounces back toward the focus. We have our F ray that goes through the focus and comes off horizontally. And comes off horizontally. And from those two, we can see we've got an intersection right there. We can see that we've got these two are intersecting at this point down here. And we can check by looking at the ray that passes through the center of curvature. That's going to go like that and bounce back along the same path. And we can see that it also intersects at the same spot. So, for a concave mirror, and this is the case of a concave mirror where the object is past the center of curvature, we get this image right here. We get an image that is, number one, the light rays actually converge here, which means that the image is said to be real. Okay, light rays actually converge at a real image. We can see that it's upside down, and the term we use for that is inverted. And this image is located. This image is located between the center of curvature and the focus. So, for an object out beyond the center of curvature, the image formed is real, inverted, and located between the center of curvature and the focus, and we can figure that out by drawing our ray diagram. Now let's take a second case. For our second case, we're going to put our object between the focus and the center of curvature and see what happens here. Well, first we have our P ray. It runs parallel to the principal axis and bounces off, passing through the focus. Alright, there's our P ray. Our F ray passes through the focus and bounces off the mirror horizontally, parallel to the axis of rotation, which is going to look about like that. And then the third ray passes through along the line to the center of curvature. So this is going to bounce off the mirror, up here and bounce straight back. And so that one winds up coming right here. Now you can see those don't quite all meet in the same spot, which just means that in my drawing the mirror surface was not quite as close to being a full circle as it was in the previous drawing. But this image will then be formed right back over here. This is our object. This is our image. So let's see what happens. So if we have our object between the radius of curvature and the focal point, then the image, the light rays actually converge, so it's real, it's inverted, and it's beyond C. Also, I didn't state this here, but you can see that this image is much smaller than the original object, and this image is larger than the original object. So that's what happens when the object is beyond C and between C and F. And then our last case, as may be obvious, is an object that's in between the focal point and the mirror. We can draw our rays again. Draw our B ray, bounces off the mirror, passes through the focal point. We can draw our F ray that passes through the focal point and bounces off straight. Now that's kind of weird. Extends backward, but it's going to go that way and then bounce off straight. All right. Now you notice, and we can do our C ray as well, that these rays don't actually converge. So then that begs the question, what's going on here? Well, those rays don't converge. So that means that a real image is not going to be formed. But if we trace them further along, so this is it bounces off the mirror this way, so if we kind of trace that backward, if we trace this one backward through the mirror, we trace this one backward through the mirror, we can see that they all converge at this point behind the mirror. And so for an object that is inside the focal length of the concave mirror, so object between focal point and the mirror, we have an image that is virtual, just like it was for a convex mirror. The light rays don't actually converge, but they appear to be coming from a source that is behind the mirror. And the image is virtual, it is upright, and it is also enlarged. That's what happens when the object is inside the focal length of the mirror. On page, I've listed out different properties for where the object is, what kind of mirror it is. Page 917 has a table that gives a nice summary of what happens for each object location and image orientation and image sized and whatnot. And that's the table. But keep that in mind. It's a handy resource to have available to you.